Good morning students. Today we will discuss about particle in one-dimensional potential box or particle in one-dimensional potential well of infinite depth. Okay, now let us consider a free electron trapped in one-dimensional potential box. See here what is meant by potential box. Potential box means electron which is trapped in a metal, electron present in a metal, or otherwise electron present in p-n junction, heterojunction. Okay, now let us consider, see here we are considering free electron which is trapped. This is the free electron which is trapped in a one-dimensional potential box. One-dimensional, I am taking only one dimension, that is along x-axis, which is having length L or width L. Now, here inside the potential box, potential is 0, and outside the potential box potential is infinite. Outside the potential box it is infinite. Next, the box is of infinite depth. The depth of the box is infinite such that the electron cannot escape from the box. Now here we want to calculate what we want to calculate. In this potential box we want to calculate how many energy states. See here how many energy states and what are the energies of those energy states. We need to calculate energies of the energy states and we need to calculate where does this electron stays. So see here what we want to calculate is in this potential box how many energy levels are there and what are the energies of each state. What are the energies of each state. Next, where this electron is present in this state. Again this E2 state, this E3 state, E4 state, E5 state, where electron stays, that we need to calculate. Okay, for that purpose we consider one-dimensional Schrodinger wave equation. So what is the one-dimensional Schrodinger wave equation? D square psi by dx square plus 2m into E minus V by h cross square psi is equal to 0. This is equation number 1. Now, electron is present inside the potential box or outside the potential box. So, see here, electron is present inside the potential box. So, inside the potential box, potential is 0. This is equation number 2. So, inside the potential box, potential is 0. Now, we'll substitute 2 in 1. So, see here, if I substitute V is equal to 0 in 1, I'll get it as d square psi by dx square plus 2m E by h cross square psi is equal to 0. So, we'll substitute equation 2 in 1. We'll get expression as d square psi by dx square plus 2me by h cross square psi is equal to 0. This we'll write it as d square psi by dx square plus k square psi is equal to 0. So what I have taken it as k square? So I have taken k square as, see here, this is equation number 3 where k square is equal to, I have taken k square as 2me by h cross square. This is equation number 4. Now, see here, this is the second order differential equation. This equation 3 is second order differential equation. So, for this second order differential equation, I can directly write solution. So, the general solution of equation 3 is, the general solution of equation 3 is psi of x is equal to a sin kx plus b cos kx. A sin kx plus b cos kx. This is equation number 5. Here A and B are constants. Here A and B are constants. So these A and B can be evaluated. So see here, these constants can be evaluated using boundary conditions. These can be evaluated using boundary conditions. Now, what are the boundary conditions? What are the boundary conditions we have? Boundaries are, one boundary is x is equal to 0 and another boundary is x is equal to L. So at x is equal to 0, we know that psi vanishes at boundaries. Wave function psi vanishes at boundaries. So psi of x is 0. So this is also boundary. So psi of x is 0 because psi vanishes at boundaries. We have seen in limitations. Okay. Now this we keep it as equation 6 and this as equation 7. Now if we substitute 6 in 5. If I substitute equation 6 in 5, I will get psi of x is 0. Psi of x is 0. 0 is equal to a sin k. X value is 0 plus b cos k 0. So which implies 0 is equal to sin k of 0 means sin 0. Sin 0 is 0 plus cos 0 is 1. So we'll get b. So implies b is equal to 0. I got constant b is equal to 0. This is equation number 8. Okay. So I got constant b as 0. Now substitute 7. Equation 7 in 5. Now substitute equation 7 in 5. Means in place of x you keep L. In place of psi of x you keep 0. So I will get it as 0 is equal to a sin kl plus b cos kl. So what I got? 0 is equal to a sin kl plus what is b? B is 0. So b into cos kl will be 0. This is from equation 8. Now I got a sin kl is equal to 0. So what I got? A sin kl is equal to 0. Okay. We'll repeat here. A sin kl is equal to 0. So here a must be equal to 0 or sin kl must be equal to 0. Any one should be equal to 0. So which one is equal to 0? So see here a is not equal to 0 because already b is 0. So if a is also 0, two constants will be 0. So two constants never be equal to never be equal to 0. Two constants never be equal to 0. So which one is equal to 0? Sin kl should be equal to 0. So implies for what value of kl? Sin will be 0. So at what value of kl? Sin 0 is 0. Sin pi is 0. 2 pi is 0. 3 pi is 0. Then I can write kl is equal to n pi. Kl is equal to n pi. So implies k is equal to n pi by L. N pi by L. This is equation number. So what is this equation number? So till here I got 8. This is equation number 9. Okay. Already we got k value. So already we got k value here. This is equation number 4. K square is equal to 2m e by h cross square. Here I got k is equal to n pi by L. So equating 4 or otherwise you can write substituting 9 in So in place of k square, I will substitute this. So n square pi square by L square is equal to 2me by h cross square. 2me by h cross square. So all e means e this side, all other terms to that side. So what happens? N square pi square h cross square divided by 2m L square. So we can write it as n square pi square. What is h cross? We know h cross is equal to h by 2 pi. So I can write it as h square divided by 4 pi square 2m L square. So this pi square get cancelled. You will get energy as n square h square by 8m L square. So E is equal to n square h square by 8m L square. So here n takes the values. See here I can write this one as En is equal to n square h square by 8m L square. This is the expression for energy. So this is equation number 8, where n can take the values. N is equal to, it can take the values 1, 2, 3, 4, so on, which is called as principal quantum number. This is called as principal quantum number, which starts from 1, 2, 3, so on. It doesn't starts from 0, remember. Okay, now, so see here, this is the energy expression. I got energy expression En is equal to n square h square by 8m L square. Okay, if I substitute, if n is equal to 1, means n is equal to 1. This is for ground state. N is equal to 1 is for ground state. So for this ground state, now what happens if in place of n, if I substitute 1, E1 is equal to, we know this is the expression. In place of 1, if I substitute, in place of n, if I substitute 1, I will get E1 is equal to h square by 8m L square. So this is the expression we have. En is equal to n square h square by 8m L square. So if I substitute 1, I will get it as h square by 8m L square. This is for ground state. This is the energy for ground state. Next, if n is equal to 2, first excited state. So see here, many students commit mistake here only. If they ask first excited state, they will go for n is equal to 1. But it is not n is equal to 1. This is n is equal to 2. So first excited state, we can write it as E2 is equal to, see here, in place of n, I am placing 2. So E2 is equal to 4h square by 8m L square. Okay. If n is equal to 3, second excited state. So if n is equal to 3, second excited state, I can write it as E3 is equal to 9h square by 8m L square. So I can write this as 4E1. I can write this as 4E3. Okay, so like this, so on. So what we have calculated, if the potential box is there, this is of width L. So the energy of the first level is E1 is equal to h square by 8m L square. The energy for the next state n is equal to 2 is E2 is equal to 4E1. Next, for n is equal to 3 state, E3 is equal to 9E1. So on. So here we have calculated the energies of different energy levels. So see here you got single expression for energy, but for different states, different energies. So this says that energy is discrete. Energy is discrete and quantized. Energy is discrete and quantized. So here energy is different for different energy levels, but you are having the same expression. So that we call it as energy is discrete and quantized. So we have calculated energy levels, energies of the energy levels. Now we need to calculate where does this electron stays. Where does this electron state? In first state, where does this exist? In second state, where does this exist? In third state, where does this exist? Okay. So now in order to do that, we need wave function psi, because the probability of finding particle is given by modulus of psi square. Okay. This we'll discuss in next class. Thank you all.